Hi, today we're presenting a paper called Automated Modeling Testbench Methodology Tested with 4 Types of PLL Models. My name is Joshua Baylor, and my co-author, Jun Yan, and I are from Renesas Electronics. I'll start by covering modeling scope and the modeling strategy used in our design groups. Then I'll introduce the PLL used in our experiment and show examples from 4 models. After, Jun will cover how he automated the test bench setup for model comparison, and then review the results. If you consult 4 engineers for their model requirements, you'll likely end up with 4 definitions. If we consulted a 5th engineer, we'd probably still be working on this presentation. Joking aside, it's important to define purpose and scope for a model as early as possible to avoid misunderstanding and misuse of the models. Our design group uses models to prototype at the architectural stage, improve simulation speed for systems, and to verify design connectivity. We can broadly divide the models into analog models that call the analog solver for electrical nets using Verilog A or Verilog AMS, discrete models that use a pure Verilog simulator, and real number models that can use system Verilog or Verilog AMS simulators. We try to avoid calling the analog solver on electrical nets in the real number models and stick to net types that can be processed by the event-driven simulation like EENet or WRealNet types. The EENet net type is a user-defined system Verilog net type provided by Cadence. In our organization, chips like power management ICs and battery management ICs tend to follow an analog-heavy verification flow, while the video signal processing chips tend to follow a digital-heavy verification flow. In the analog-heavy flow, we're really looking for analog-to-analog interactions between blocks, where in the digital-heavy verification flow, we may have much more complexity in the digital core and relatively simple levels of complexity in the transmitters and receivers, and we may need PLLs to do some multi-clock domain digital verification on our digital-heavy devices. We were looking to improve our verification coverage in the video signal processing product line, and we had multiple existing PLL models to choose from. Unfortunately, these models were designed with different purpose and scope and mainly meant as prototyping models or digital simulation crutches. The AMS models are generally too slow for full chip verification, and the open loop discrete model didn't provide the necessary coverage for verification targets. The real number models were developed to bridge the gap between performance and coverage, and the automated comparison tools that Jun will talk about later were used to compare the speed and accuracy of the models. The PLL used in our experiment features both digital and analog supplies, some input bias current, the reference clock input, reset control, power down control, some controls for the charge pump current, and of course the PLL output clock and a lock indicator. Next, we'll describe the 4 PLL model examples, the open loop, closed loop, Verilog AMS, and the closed loop real number model with EENet. The open loop real number model is the simplest of the models. It provides basic functionality without covering any of the internal implementation details. The charge pump and loop filter behavior are not modeled, and the VCO simply calculates an output frequency based on real-time measurement of the reference clock. Settling response and lock detection are not modeled, and this level of detail is insufficient for spread spectrum PLL usage. The closed-loop real number model was made to show accurate settling behavior while maintaining the speed and convenience of pure Verilog simulation like the open-loop model. While the analog loop parameters are accurately captured, the model doesn't have a one-to-one hierarchy match with the schematic. The charge pump, filter, and VCO are combined into one block to avoid having to pass voltage and current information on one net, which can't be done with basic Verilog net types. A drawback of this approach is that the model is harder to maintain for charge pumps and filters with different numbers of control settings. In the Verilog AMS model, we can model everything from the bottom up, giving separate and accurate models for the charge pump, loop filter, and VCO. We can maintain the complete hierarchy and get very accurate performance, the main drawback being that since electrical net types are used, the simulation is much slower since calling the analog solver on an electrical net is much more expensive than an event-driven solver. The closed-loop real number model with EENet also models blocks the one-to-one correspondence to the schematic. Using the EENet package components, it's relatively straightforward to construct the loop filter and charge pump models. The benefit of the real number model with EENet over the AMS model is that it runs without invoking the analog solver and therefore runs much more quickly while maintaining reasonable accuracy.
In the next, I'm going to talk about how to create modeling testbench with automation. The input of the automation scripts consists of two parts. The first part is the config spreadsheet, which is to specify the cadence library path and also the name of design blocks for DOT. And the other part is the DOT schematic and the model which are available in the cadence library. The script is mainly written with Python, but also have a skill script which can automate testbench creation, including stimulus model template and the testbench connectivity. There are two testbench options. One is with two DOT, which put model and schematic view side by side. The other is with one DOT, which we can configure DOT as either the schematic or model and run separately. For switching DOT, since model is running much faster than schematic, putting schematic along with model will make the simulation run much slower compared to running model by itself. So one DOT option is more efficient and preferred compared to the two DOT option. Here is an example of how modeling testbench looks like. There are two types of stimulus modules. StimHW is a hardware module which have the same ports of the DOT and directly connected to DOT. And it contains hardware components such as voltage drivers, capacitors, resistors, switches to emulate silicon validation PCB board. The other module is named the StimSW is the software module which has no ports, but it uses test sequence to drive components in the hardware modules. Then I will explain more about hardware and software modules one by one in the following two slides. For the hardware module, the biggest challenge is how to choose the right drivers for different models, such as AMS or real-number model. There are two options, but with trade-offs in between. For option A, we can use same AMS drivers to drive both AMS models and the real-number models. As AMS drivers provide electrical output and real-number models need a real-time input, E2R connect modules need to be inserted in between. For option B, instead of using connect modules, we can use dedicated digital drivers to drive real-number model. On the right side is an example of stimulus code based on option B. With different configs selected, we can choose either digital drivers or AMS drivers. In this slide, it shows what is exactly inside AMS drivers or digital drivers. In AMS drivers, we use AMS modules such as voltage or current source to drive analog signal and set digital value on rack type, and then assign to corresponding wire type DOT port. Supply sensitivity is needed for digital ports, and it is used for the D to A conversion if it is connected to the electrical node. Inside digital drivers, we have universal double rail drivers to drive either voltage supply or bias current, as they are both defined as real net type in real-number model. Digital signal is driven in the same way as AMS drivers, but without supply sensitivity. The software module is shared between AMS drivers and digital drivers. To do that, firstly, we are using the same task name and arguments between the corresponding AMS and the digital driver modules. Secondly, we need to have the same instance name for the AMS and the digital drivers. We have monitors to measure the mean, max, or peak-to-peak value of selected DOT output signals. The monitor module is written in system Verilog, which can only take real type or digital type as the input. Real-number models can be collected to the monitors directly. However, to collect to the AMS model, we need to insert a A2D module to convert electrical type to digital type. Instead of using F delta function to do the conversion, we are using an analog clock module to generate a digital clock which aligns with analog time step, and use this clock to sample the electrical signal. This method can enable accurate conversion without slowing down the simulation. This slide shows the simulation results of the 3 closed-loop models. As you can see in the waveform, the VCO control signal, which is used to show the settling response, correlates very well between the 3 models in the comparisons. This table shows the final comparison of the 4 models, including 1 AMS model and 3 real-time models from different angles. We also color the rating with high as green, medium as blue, and low as black. For the driver type, AMS model is using AMS driver, and the other real-time models are using digital driver. AMS model is difficult to develop due to the conversion issue and the slow simulation optimization. Closed-loop real-time model is also difficult as we need to deal with the mathematics equation. The other 2 are comparatively easier. AMS model and the ENet model don't need us to change the schematic, which means we can truly verify the connectivity of some modules. Next, according to the last slide, the 3 closed-loop models can accurately model the settling response of PLL loop. And for the simulation time, all 3 real-time models are much faster than AMS model. Before doing the experiment, to run DMS verification, we were using open-loop real-time model, but we switched to the ENet model because it has many additional advantages without adding too much overhead to the simulation speed. Here is conclusion of today's presentation. For DMS verification, we choose ENet model because it runs fast. We can truly model PLL settling response and the configuration through the control ports. No need to change the connectivity of PLL subblocks in the schematic. Also, it's not difficult to create by using ENet packages provided by Cadence. Still, we need AMS models for a few analog-related simulation run from the top-level verification. Thanks for attending today's presentation. Please let us know if you have any questions.